Today we're going to look at empirical and molecular formulas. A few things we want to be able to do by the end of this lesson. First of all, define what are empirical and molecular formulas, and then be able to convert from one to the other. So if I give you the empirical formula, can you give me the molecular formula, and vice versa? Okay, so we're going to jump right in here. So first we got to define these things. So let's take a look at this little table here. So I have four molecular formulas in the first column here, and they're empirical formulas, right? So these go together. The left one and the right one, left, right, left, right, left, right. Okay, so what I'd like you to do before you move on in the video, so I'm going to ask you to pause it in a moment here. I want you to use the information in that table to define what a molecular formula and what an empirical formula are, okay? And also think about, you might want to use the term ratio in your definition, right? A little hint there. And I also want you to think, can two different compounds have the same empirical formula? So, meaning, can they, two different compounds have different molecular formulas but the same empirical formula? How do you know? And use an example. There are examples, in the table above you can use. Hint, hint. Okay, so pause the video take about 5 minutes. Define those two terms, molecular formula and empirical formula, based on what you see in the table, right? So remember that for C2H4, that's the molecular formula. Its empirical formula is CH2. All right, so there's basically four examples of molecular versus empirical formula. And I'd like you to just define what those two things mean and answer question number 2. So go ahead and pause the video. Seriously, pause the video. Okay. Hopefully you paused the video and actually define these terms in your own, because remember, if you come up with your own definitions, they're going to stick better than if I just tell you them, okay? It is true. It's been proven. So let's define these things. A molecular formula tells us how many atoms of each element are present in one molecule of the compound. Okay, so if we look at our examples in the previous slide here, right? C2H4, in one molecule there are 2 carbons and 4 hydrogens, right? In H2O, you know that one, there's 2 hydrogens and 1 oxygen, right? So it tells us how many atoms are in each element are present in one molecule of the compound. So in one molecule of H2O, right, there are 2 hydrogens and 1 oxygen. Whereas the empirical formula, right, is written as the smallest whole number ratio. Okay, so the elements appear in the smallest whole number ratio. It's like simplifying a fraction. Okay, so I'm going to go back. If we look at this top example, right, C2H4, right, we wouldn't keep a fraction as 2/4. We'd keep it as 1/2, right? So we can simplify C2H4 down to CH2. And it doesn't get simpler than that, right? Having a 1 there, you can't get simpler than that. Another example, right? C11H22O11, right? We can probably see, you can divide all those by 11, and you get CH2O, right? The simplest whole number ratio compared to, remember that this represents the actual molecule. If I have one molecule of whatever this is, right, it has 11 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms, right? But the empirical formula just tells us the simplest whole number ratio. So CH2O, meaning for every 1 carbon, there's 2 hydrogens and 1 oxygen, which is true, right? But it doesn't tell us the whole number like the molecular formula does, okay? So molecular formula tells us how many atoms of each element are present in one molecule of the compound, whereas the empirical formula is the smallest whole number ratio. And hopefully you notice two different compounds, they can have the same empirical formula, right? Consider these 2 compounds, which were in the table in the last slide, C2H4 and C25H50, right? Both of them have the same ratio of 1 to 2, right? 2/4 is the same as 25/50, right? Um, so both of those can be reduced or simplified down to CH2. So remember, these molecular formulas represent, okay, so in this compound, there are actually 25 carbon atoms and 50 hydrogens, but it's the same ratio as in C2H4. It's a 1 to 2 ratio, right? The empirical formula for both is CH2. Right, this is basically what I just said. Whereas C25H50 has more atoms per molecule, right? A lot more atoms. The smallest whole number ratio is the same, meaning they have the same empirical formula. Okay? And again, don't forget, you can always pause, rewind, listen to me, go over these again. There's also the readings to do, right? Don't forget. So I'm going to go fast, but you have control over the speed. All right. So how do we get the empirical formula from the molecular formula? And then we're going to do it the other way. So to derive the empirical formula from the molecular formula, you must simplify the subscripts. All right, we kind of already did this, right? So there's no equation for this. It's just simplification, right? You want to get that lowest whole number ratio. So let's do some examples. What is the empirical formula of C6H12O6? Okay, so I mean, I probably don't need to write this out, but why not? It's fun. So if we have C6H12O6, right, you might notice 6, 12, 6. What can I divide all of those by? Well, 6. Okay, and if I do that, 6 divided by 6 is 1, so it's just C. 12 divided by 6 is 2, so we get H2. And then 6 divided by 6 again is just 1, so it's O. So it's CH2O. All right? This is empirical. This is molecular. Okay? Let's go back to the slide here. So, right. So, again, we're just simplifying when we're coming up with the empirical formula, right? Pretty basic. Let's do a couple more. Maybe you can do these right before I do them, right? So what are the empirical formulas of, 2 more examples, NH3 and then C6H6. Take a minute. So hopefully you noticed NH3, already simplified. That is the empirical formula. Sometimes the empirical and molecular formula are the same because the molecular formula is as simple as it gets, right? So NH3, it's a ratio of 1 nitrogen to 3 hydrogens. You can't get simpler than that, right? 1/3. You can't simplify that any further. 1/3, however you want to look at it. But this one, hopefully you noticed, right? What can we divide both those numbers by? Well, 6, right? So C6H6, it's a 1-to-1 ratio. So the empirical formula is just CH. That's it. Okay. It really doesn't get more complicated than that, right? You're just looking for, I guess, what, the greatest common factor, the denominator? I don't know. Right, whatever you can divide the subscripts by evenly, right, to get those whole number ratios. Okay. Now we're going to go the other direction. From deriving or getting the molecular formula from the empirical formula. Now this is going to take a little math. This is not as simple, all right? And you need to be provided with a little extra information. So first thing you're going to have to do is calculate the molar mass of the empirical formula. I'm going to show you, but remember, molar mass, that's where you add up the masses of all the atoms in the compound, okay? We've done that multiple times, right? Then you're going to divide the molar mass, right, of the substance, which will be given to you, right? That's the molar mass, the actual molar mass of the whole thing, by the molar mass of the empirical formula that you just calculated. Finally, you will multiply the empirical formula by whatever number you get from step 2 after you do that division, all right? So this will become a little more clear when we do a couple examples here. So, right, first example, The empirical formula of a molecular substance is CH2, right? Definitely empirical, can't get smaller ratio than that. The molar mass of the substance is 70.05 grams per mole. All right, so it wants us to determine the molecular formula of this substance. Okay, so let me just write this down before I switch screens here. We have CH2 and a molar mass of 70.05 grams per mole. All right, got my information here. Okay, so first step we want to do, right, if we remember, calculate the molar mass of the empirical formula. So this is our empirical formula, right, CH2. Okay, you will need your reference table handy unless you have all of these masses memorized. You might, for these two at least, right? By this point, we've done it so much. So carbon, right, has a mass of, and you can round up here. You don't have to use the 12.011, right? You can just say carbon's 12, and there's only one of them. Okay, we're going to add that to our two hydrogens, right? And each hydrogen has a mass of about 1. Now, if you don't know where these numbers came from, the 12 and the 1, it's the, let me show you really quickly, right? You should have your reference table handy. There's also one on Google Classroom. Let me show you that one actually, because that's the one that's going to be more accessible to you. You can always just type into Google chemistry Regents reference table, and it's the first thing that pops up. But I did provide it for you under resources. Okay, so go here, right? Syllabus. Nope, that's not the right one. Oh yeah, it is reference table right there. Okay, reference table. Boom. So you're going to want to look at the periodic table. Okay, so if you're wondering where the 12 came from, there it is, right? It's the upper left-hand corner, right? Atomic mass is what you're looking at on the periodic table. And then remember we rounded that to 12. And then hydrogen up here, okay, it's 1.00794. You can just call it 1 for our purposes. All right, so in case you forgot where to get those numbers, you need the periodic table. All right, okay, back to our problem here. So that's where these numbers came from. So if we add those up, right, 12 plus 2, can do that one, that'd be 14. And technically, right, it's a molar mass, so the units are grams per mole. Okay, you could also say that it's 14 atomic mass units if you're talking about the weight of the molecule itself, right? But right now we're talking about molar mass. Okay, so that was our first step. That was step 1, something like that, right? And now we want to divide the molar mass of the substance, which is given to us. It has to be given to you. You're never going to know the actual molar mass of the substance, right? By the number we just came up with, by the molar mass of the empirical formula, right? So this was given to us. This is the molar mass of the substance. This is the molar mass of the empirical formula. So in step 2, right, what we're doing is dividing the mass given to us, so this is the actual molar mass of the substance, by the molar mass that we calculated of the empirical formula, right? So molecular, empirical. This will always be given to you. This you have to calculate based on the formula, which is what we did in step 1. Okay? So if we do this out, oh geez, I don't have a calculator. But I do on my phone. So we're going to do, probably going to beat me to this one. Do I have a calculator? There it is. So 70.05 divided by 14 basically gets us to 5. Okay, if you round, it's about 5. All right. So that was step 2. Step 3, if we go back here, we multiply the empirical formula by, right, I should say by the number obtained in step 2. Let me fix that in real time. By the number obtained in step 2. Save that. Okay. Oh, let's go back here. All right. Okay, so finally we want to multiply the empirical formula by the number obtained in step 2. Okay, and what does that mean? Well, here's the number we obtained in step 2. There's the empirical formula. So if I multiply the subscripts by 5, I should get 1 times 5 is 5, so C5, H10, because 5 times 2 is 10. So this is the molecular formula. Okay? Yeah, that doesn't get more complicated than that. So quick recap, right? We were given the empirical formula, right? This is empirical. And the molar mass of the substance, right? The actual molar mass. First, we had to calculate the molar mass of the empirical formula, right? Then we divide our given molar mass by the molar mass of the empirical formula. That gives us a number, right, that we multiply the empirical formula by to get our molecular formula, okay? And remember, right, something with empirical formula of CH2 could have an infinite number of molecular formulas, right? C2H4, C3H6, C4H8, on and on forever, right? So we need this number here to really figure out what our molecular formula is going to be. All right, cool. So something you can do, take a minute before you move on to the homework, right? Some practice problems here. If you can do these 3, you're good, right? So you want to define empirical and molecular formula, be able to give me the empirical formula when given the molecular, and then derive the molecular formula when you're given the empirical formula and the molar mass of the substance. So go ahead and pause the video here, try these 3 questions, unpause, and I will quickly go over them. Okay? So take a minute, do that now. All right. So, empirical formula, right? That's the smallest whole number ratios, right? So formula, we can go back to the actual definition here. Right, empirical formula, elements appear smallest whole number ratios. Molecular formula, how many atoms of each element are present in one molecule of the compound. Okay, so hopefully you got those down. What's the empirical formula of sucrose? C12H22O11. Hopefully this didn't trick you. You can't divide all 3 of those numbers by anything evenly, right? So that is the empirical formula of sucrose, right? The C12H22, those are nice even numbers that you could have divided, but that O11 kind of screws it up, right? There's no whole number we can divide into 12, 22, and 11 evenly, except for 1, but that's not going to change anything. So that actually is the empirical formula for sucrose. Number 3, a compound has a molar mass of 90 grams per mole. Okay, I'm going to write that down, 90 grams per mole. And a empirical formula of CH2O. And it's asking, what's the molecular formula? Well, let's do this, right? Remember our steps. Our first step, we need to know the molar mass of our empirical formula. So we have 1 carbon, which is 12. Remember, these numbers come from the periodic table. I'm going to add that to my 2 hydrogens, each of them having a mass of 1. Okay? Really, remember, it's 1.007, whatever. But we can round these to whole numbers. And then there's a little oxygen there, which is one of them. Oxygen has a mass of about 16, right? This is 15.999, but we can use 16. So if you add all these together, 16 plus 2 is 18, plus 12 brings us to 30. Okay, 30 grams per mole, right? And you could probably, right, this one's going to be easy. 2, we divide the, it's always going to be the larger number by the smaller number, right? Because you should get a whole number out and not a decimal. So we divide the molar mass of this actual substance, which is 90, by the molar mass of our empirical formula, which is 30, right? And this one I don't need a calculator for. Okay, 90 divided by 30, is 3. All right? Now, this is the number we multiply our empirical formula by to get the molecular formula. So, our molecular formula, C3, H, 3 times 2 is 6, H6, O, 3. That's our molecular formula. Okay. Yeah, that's about as difficult as it gets. So, but feel free, again, this is the first time you're doing it, so feel free to rewind, watch the video again, do the readings. There is a homework tonight, right? 10 multiple choice questions. They're all very similar to this. It's either you're coming up with the empirical or the molecular formula. Make sure you submit that by midnight, right? We're not doing 9 a.m. deadlines, we're doing midnight. So you need to actually do the homework during the same day. That's just for me, so I can get feedback quicker, so that I can, tailor those meetings we have, the optional meetings on Zoom, um, to what we need. Okay, so that's going to be it for this video. Go ahead, do the reading for a little extra, and then complete the homework. And I will see you on Zoom or in my next video. All right, stay safe.